Welcome to the next lecture on digital communication. In this lecture, we will study the error control coding. What it means. Before that, I would like to show you the general block diagram of communication system. Here is the basic model. You have a discrete source. Okay. So even if you don't have discrete source, suppose you have analog source, then you will have to go for sampling, quantization, right, and then PCM, and you will have then definitely a binary discrete source. In some cases it may be a readily available discrete source, like in data communications. Then you have something called channel encoder, which we will introduce now. What you have done till now is you have a modulator, right, like a BPSK modulator, QPSK modulator. Then you have a waveform channel, as we have done, right. This was SI of t, and this is W of t, and this was X of t, and X of t is the output of the channel. Then you had detector, which the design which we have done, like BPSK demodulator, QPSK demodulator. But what we have done in BPSK lecture, if you see, suppose you had, this is your BPSK symbol, and we told that if receiver receives the symbol here, it can make errors also, and probability of error was Q function of 2EB by N0. Now what is the way to decrease probability of error? If you look at the expression, the graph, so this is the SNR or EB, this is the probability of error. So definitely the only way with modulation, the only way to reduce probability of error is to increase the EB, to increase the energy of the bit. But you cannot increase it tremendously, especially in cases of, suppose, mobile communication. Your SNR is quite low, okay, maybe somewhere here. So if this is your SNR, then definitely it is a significant error, right? Significant error. Maybe in case of large receivers, suppose satellite communication, you may afford to have very large power, so then you can bump in lot of power, you can increase EB so that you get less probability of error, but you will never get it to zero. But in usual point-to-point communication or mobile communication, small handheld devices, you cannot increase power too much, so you need to have some other scheme. That scheme which decreases the probability of error further, that's what we call here channel encoder, right? And then equivalently we have here channel decoder. Okay, it will become more and more clear as we will proceed further. But I have written one more thing. I have written here discrete channel. Sorry. Because if you look at this point, you have binary zeros and ones available. Even channel encoder, what it does is it adds extra bits, as you will see. So this also is, there is only binary numbers here, and then you modulate it, then you do line coding and BPSK modulation, you multiply it with the cos, then there is a channel, waveform channel, then there is a detector, you detect the symbol. After you detect the symbol, you take a decision whether it is 0 or 1, you again get 0 ones here. So you can treat that this whole setup can be written in a very simple way. Suppose if you take a binary case where you have just 0 and 1, which is the most practical case, so you can treat this whole setup as you have 0 and 1, you need to transmit these two. And what can channel overall do? See, if you look at this part, so what you can what you can see is that you have here, suppose SI of t, this is an X of t, noise is W of t, which you have done recently. But if you look at this point, you have zeros and ones. So if you look inside this box, discrete channel box, sorry, what is the effect of noise? And the effect of noise is to change the waveform. But what is its effect on bits? The effect of noise on bits is to change 0 to 1, 1 to 0, right? So I can model it like this. So the channel can change 0 to 1, this is 1, or 1 to 0, these are the errors, or there may be no error, so channel may transmit 0 as it is and transmit 1 as it is. And this is a random thing, so it will happen with some probabilities. Suppose the probability that 0 changes to 1 is P. Again, probability that 1 changes to 0 is P. So probability that 0 is not altered, is not changed, is 1 minus P. And probability that 1 is transmitted as it is 1 minus P. If you call this as X, this as Y, this is input symbols, this is output symbols. So this channel is called binary channel because there are only binary bits. It's called symmetric also. Why symmetric? Because probability of 0 changing to 1 is same as probability of 1 changing to 0. Otherwise you could have chosen this as P1 and P2. That is difficult to analyze. We assume it is binary symmetric channel. This is a best model. BSC is the best model. In fact, you can even compute its capacity easily. I have shown you all the bits and pieces to compute that. Now, but we are worried about another thing. How can we reduce the error? So one of the possible ways something called repetition coding. See, if you transmit your binary sequence, suppose this is your message signal. Sorry, message bits. If 1 change to 0 or 0 change to 1, it is lost permanently. Okay, you cannot recover it. We want to protect it. So what repetition encoding does? So repetition encoding says that if you have to transmit 0, let's take a very simple case. Don't transmit it once, transmit it 3 times. 0, 0, 0. If you have to transmit 1, don't transmit just 1, transmit 3 ones. Okay. This is the coding. It's called encoding. Okay. I have encoded. Now what will receiver do? Sorry. See, now this 0, 0, 0, 1, 1, 1. So to transmit 0, you will transmit these 3 bits over the channel. It's also called a 3 channel uses. You are using the channel now 3 times. Okay. And so you are mapping k is equal to 1 message bit. Okay. This is the message bit. You chose it from this message signal. And you are mapping it to n is equal to 3. This is called channel code also. Channel coding. And this procedure of, this procedure of mapping a message bit 0 to 3 bits and mapping a message bit 1 to 3 ones, it's called this, the device which does it is called channel encoder. Okay. So you can think of channel encoder in this case. You are passing in 0, you get 0, 0, 0. You are passing in 1, you get 1, 1, 1. Very simple channel encoder. Now what will the receiver do? What will happen? So, when you will transmit these bits, suppose channel is such that only 1 bit error happens. Only 1 bit error happens. Okay. If there is only 1 bit error, you will see that we can have a scheme where we can completely recover all the errors. See how. So when you transmit 0, receiver receives, suppose there is one error 0, 1, 0. You transmitted 0, there is an error at the second position. You actually transmitted 0, 0, 0, but second position is an error. So receiver will use something called majority rule. But what is majority rule? Receiver will say count number of zeros and count number of ones. Whichever is greater, decide in favor of that. So here we see that number of zeros are 2, number of ones is 1. So decide in favor of 0. Now, if channel is very bad and it changes 2 bits, then suppose we can receive 110, the receiver will make wrong decision. What is the solution? You will see that for one message bit, take n is equal to 5. Okay, so that is, instead of 0, transmit 5 zeros. Instead of 1, transmit 5 ones. Now see, even if there are 2-bit errors, suppose you transmitted 0, but receiver receives 1 0 1 0 0. But number of zeros is 3, number of ones is 2, so 3 greater than 2, so receiver will decide in favor of 0. Suppose, okay, it's here 1 1 1 1 1. If you transmit 1, instead of 1 you will transmit 5 ones. Receiver will receive, suppose 0 1 1 0 1. So number of ones is 3, it will decide 1. But again here, if there are more than 2-bit errors, then you will definitely get again error. But you see the error rate has decreased, right? This is called error control coding also. But it is a very simple coding. But there is a loss in it. Suppose this is your source of bits, binary source. Binary source can be output of pulse code modulation also, right? After you do sampling and quantization and then you do pulse code modulation, the output of that will be definitely a binary source. There will be a particular rate at which the bits will come out of that source, right? There will be a particular rate. Let's call that rate as RS. Bit rate of information source. Suppose the source may emit 100 bits per second, 200 bits per second, or even more, right? It's called bit rate. But there is another rate which is called code rate. Code rate is number of message bits divided by number of, you can say, encoded bits, which is here k by n. Suppose in first example k was 1, you were choosing one message bit, n was 3, so this k by n is, which is the, you can say, code rate, it is 1 by 3. So what is the overall rate? Overall rate is basically, the overall encoder rate will be RS divided by k by n. This we call as R naught, okay, or n over k RS. Now if you look at this k by n, as n goes to infinity, k is fixed, k is always 1. This k by n becomes 1 by n. As n goes to infinity, it becomes 0. So you get a code rate closer to 0. Right? So this is the trade-off. This is the loss here. We are able to, so in fact, if you choose n to infinity, you will definitely get 0 error. Suppose instead of 0, you are transmitting infinite zeros. It is very, very unlikely that channel is so bad that it will change all the zeros to 1. Right? And especially you have infinite. Suppose you take 10 to the power 1000 zeros you transmit for 1 0. It is very unlikely even half of the bits change to 1. So definitely in this case, your majority rule will work easily. Number of zeros will always be greater than number of ones, whatever be the channel. right? The practical channels will not change 50% of bits. But what is the loss? The rate is 10 to the power minus almost 0. So it means that you are not able to transfer anything. So that is where we need something called intelligent channel coding. Can we do better? Is there any other thing other than repetition coding? Okay, so that opens the door of something called error correction coding or error control coding. To begin with it formally, we will first of all have some notation. We have here everything in binary. So we have a modulo operation plus, which is the XOR operation. I will denote it by simple plus. So 0 plus 0 is 0. 0, this modulo operation 1 is 1. And 1 plus 0 is also 1. But 1 plus 1 is 0. Okay. And in case of binary, 1 minus 1 is same as 1 plus 1, which is 0. That is the difference between binary arithmetic, and so we will need this arithmetic very often. And we will begin with something called linear block code. This is the first and historically also one of the earliest error control coding scheme, channel coding scheme, by which we can so what is the basic thing? We want to control the error. If you recall the repetition coding, you were choosing message bit one at a time, and this was your n is the channel code length or the encoded length. So the k by n, so this k was fixed, it is n, right? Now what is the basic logic is, if we choose k as function of n, that is, this how many message bits we will take will depend upon what is the code length we want. This is a little bit mathematical concept here. So what is the effect on this? The effect is that if you take limit n goes to infinity, this no longer will be now 0, because when you are taking n to infinity, this k of n is also depending on n. We can choose mathematically k of n and n in such a way that the limit of as n goes to infinity of the ratio is some fixed positive number, non-negative number in fact. So it can be strictly chosen greater than 0. So we will get code rate which is non-zero always, and we can take very large n. You just hold on to become clear later on. Now here is the linear block code we will take. So we first have a message bit. Message, we can say message can be represented by, so message bits we have, suppose m0, m1, m of k minus 1. As an example, if your message bits are 0 1 0 0, so m0 is 0, m1 is 1, m2 is 0, m3 is 0. So your k is here 4. Okay, message bit length. And I can represent overall message as a vector as m0, m1, m2, m3 up to m k minus 1. Okay, as an example, I can represent this m as 0 1 0 0. Now this is a k bit message, and how many different messages we can have? We can have 2 to the power k distinct message blocks. See one note here. I deliberately teach error control coding. There are two reasons. One is it's very important. Second is that computer science people will be very much comfortable with it. There is not much communication now. Okay, it's binary things and they are very much comfortable with it. Now let's suppose I take this same example. M is equal to 0 1 0 0. Okay. I want to transmit or encode it in such a way such that the errors are decreased. So what can I do? Suppose I do this thing. This is my M0, this is my M1, this is my M2, this is my M3. Let me do one thing. Let me do M0 XOR with M1. What will be that? 0 plus 1, that is 1. Okay. Then I will do M1 with M2, that will also become 1 plus 0, that is also 1, and M2 with M3, that will become 0 plus 0, that will also become 0. Now what I will transmit is not the message, but rather I will do one thing. So starting from this point I will write 0, then 1, then 1, then the message 0 1 0 0. It has now two parts. One is these message bits and these three extra bits, which we also called as parity bits. I will just demonstrate one example. Suppose there is an error. There is an error in the message signal. Suppose error is at this place. That is this 0 changed to 1. So it will be 1 0 1 0 1 1 0. Okay. Receiver knows that first three bits are parity bits generated in this way by adding message bits particularly. So receiver can easily do. So this 0 is generated by taking M2 plus M3. So this is M0, M1, M2, M3. Now if you take here M2 plus M3, that is 1, but here it is 0. So even at this point receiver comes to a conclusion that there is an error. It has detected the error. Similarly, receiver knows that the second bit is M1 plus M2, right? So M1 plus M2 is 1. It is 1, is correct. And the third one is M0 plus M1. That is here M0 plus M1. That again is correct. So only this one is wrong. Okay. It is here 0, but it is coming 1. Right? How will it come 0? The only way it will come 0 is that this 1 here should be 0. So receiver, based on the parity bits, corrects also. Say this is the correct, we call code word, and hence the message is 0 1 0 0. See, this is the message and this is called code word. See, what are we doing here? We are taking here k is equal to 4 message bits at a time, and we are generating n is equal to 7 channel bits, channel code bits. Okay. Now we will give it a general shape. So here is the notation for it. And one more thing is, if you look at the code of this message, part of the code I will represent by C. Okay. So part of the code contains message bits also. These 4 bits are message bits also. Such codes which contain message bits as it is, as a part of code, they are called systematic codes. Okay. Now let the code, we call it code word also, C equal to C naught C1 up to Cn minus 1. Okay. So it's an n length vector. Now part of the code is actually, they are the parity bits. How many parity bits we add? If you see, n minus k, right? So let they be represented by b0, b1, b of n minus k minus 1. I represent that by b vector. So we can easily see that the code word C can be written as a vector B concatenated with message vector. This means concatenation, that is, you are combining two vectors. Okay. Or, to write it in details, we can write, so this C is C0 up to Cn minus 1. So you take any of the bit Ci will be either equal to Bi for I equal to 0, 1 up to n minus k minus 1. So because there are n minus k parity bits, or it will be equal to m of I plus k minus n for I is equal to n minus k plus 1, n minus 1. Okay. Okay, it will become more clear with examples. Don't worry about it. Let's again take this. We had taken m is equal to 0, 1, 0, 0, right? And we got 3 parity bits as, if you see here, that is 0, 1, 0, 1, 1, right? How did we got those parity bits? Let's see it carefully. So the first parity bit B0, we had chosen M0 plus M1, right? B1 as M1 plus M2, B2 as, I am writing it deliberately in this way, M2 plus M3, right? So there is another way to say it. I can write here 1 times M1, or not 1 times M0, 0 times M2 plus 0 times M3, right? Same, 0 times M0 plus here 0 times M3, 0 times M1 plus 0 times, M0, M1 plus this, right? Sorry. So in other words, parity bits are formed by combining different message bits. Okay. So in general, ith parity bit will be generated from combinations of different message bits. So M0, M1, M2 up to Mk minus 1. Okay. So I will multiply each of these message bits with some coefficient. Suppose I here write P0i XOR P1i XOR P2i, so on so forth, and here I write Pk minus 1i. Okay. Sorry. Now these PIs Pij I will write, in fact, they will be having value 1 if Bi depends on Mj and 0 otherwise. Like here, this we can treat as P00, right? It is 1. So here P01, it is also 1. But here P02 is 0. And here P03 is also 0, right? So here it is P10 is 0. The first I means the ith parity bit we are computing, and J means that the jth message bit, does it depend on it or not. Okay, so in this way this Pij are chosen, and we can easily give it a a matrix shape. But before that, we now have three things: message vector, right? I again recall M0 to Mk minus 1. Parity bits are generated as the above procedure: B0 to Bn minus K minus 1, and code word bits as C0, C1 to Cn minus 1. Okay. Now this operation Bi is equal to this, we can also think of, see, if you look at it, it is B0 is equal to, I will write it in detail so that it becomes clear for you. B0 is equal to P00 M0 plus P10 M1 plus Pk minus 1 0 Mk. Okay. Similarly, B1 is equal to P01 M0 plus P11 M1 plus Pk minus 1 Mk. So on so forth up to B n minus K minus 1 equals P0 n minus K minus 1 M0 plus P1 n minus K minus 1 M1 plus P K minus 1 n minus K minus 1 Mk, right? This is how each parity bit is generated. So this can be easily given a matrix formulation by defining a P-vector matrix. It's called coefficient matrix, by taking elements P00, P01, P0 n minus K minus 1, then P10. I am taking these rows into the columns here because we have to multiply it in a particular fashion. You will see that soon. P11, P1 n minus K minus 1, so on so forth. Pk minus 1 0, Pk minus 1 1, Pk minus 1 n minus K minus 1. Okay. Now you can see that the above relationship B can be written as M times P, right? Just if you check it, if you take M, M0, M1, Mk minus 1, P00, P10, Pk minus 1 0, right? So you will see that you have to multiply it with M0, P00, M1, P10, and Mk minus 1, Pk minus 1, and you will get the required parity bits. Okay, so B is equal to M times P, right? Where this P is called coefficient matrix. These are the coefficients. Go back here. These are the coefficients which will decide whether the coefficient is 1 or 0. That will decide that which message bit I should add up together to get a parity bit, right? So hence the code word is, as I told, concatenation of this parity bits and message bits. Okay, which means it is a concatenation of MP with M, right? And if I take this M as common, as M vector, I get a concatenation of P matrix. Then what will be the next thing? That will be identity matrix. Okay, IK means K cross K identity matrix, because you are having M is a K vector message. So when you will take it as a common, and it's like in scalar you get a 1. Okay, instead of 1 it is IK. Okay, so you have now C is equal to M times PIK. Now this matrix P concatenated with IK is, what is the dimension of this? See, if you look at this P matrix here, P matrix is K by N minus K, right? See, there are K rows, 0, 1, 2 up to K, and N minus K columns, right? So this P is K over N minus K. This is K over K. So the overall will be K over N, right? This matrix is denoted by G, and it is called a generator matrix. Why generator matrix? Because we can write now C is equal to mg. It appears as if, given a message bit and given a generator matrix, you multiply message bit with generator matrix, the resulting code word, the resulting thing will be a code word. It is as if this matrix G generates the code word. Okay, or it is simply referred to as code. Now comes here the reason of calling it linear block codes, because if you have, suppose you have a message M1, right, and you multiply it with generator matrix, it will have some code word, suppose C1. Similarly, you have a message M2, multiply generator matrix, you will get a code word C2. When you add them up, M1G plus M2G, you will get M1 plus M2G. Now M1 XOR M2 will be another message. Okay, so this can be some other message, suppose M3. So this will be another code word. Okay, so we call it that the operation is closed under the modulo addition. Okay, you add two code words, the third thing will also be a code word. There is there is another way of combining the matrices. So see, we combined this P with IK, we got a G, and this G is a matrix by which you can generate the code words by simply multiplying the message bits. Okay, now if you do this thing, if you first write I of n minus k, what is I of n minus k? Again, it is an identity matrix with n minus k rows and n minus k columns, and then you take P transpose. See, P was k cross n minus k matrix, P transpose is n minus k cross k matrix, right? So if you combine the two matrices in this way, now this will be n minus k by n matrix, right? This is given another symbol h, and we call this matrix as parity check matrix for some reasons which you will see soon. Parity check matrix. And we have now a very special property. Let's compute H G transpose. See, H is I n minus k concatenated with P transpose. G was P concatenated with IK. Now G transpose will be P transpose concatenated with IK, because IK transpose is same as IK. Identity matrix. Okay. Now what will we get? We'll multiply it properly. So this I n minus k and P transpose will be P transpose plus, and P transpose times IK will be P transpose, because they are identity matrix. It's just like a 1 in scalar case. Now what is P transpose plus P transpose? See, you are, suppose this is P00, P01, so on and so forth, P10 plus P00, P01, P10, so on and so forth, right? So what will you get? P00 plus P00, P10 plus P10, P01 plus P01. You are multiplying, two bits of same, you are multiplying the same bits. See, suppose we have a bit b, or some p naught is a bit. P naught plus P naught will always be 0. Why? Because either P naught is 0, then obviously 0, or P naught is 1. 1 plus 1 is 0 in binary case, in modulo 2 case, right? So P transpose plus P transpose is adding element wise two matrices with itself, right? Each element is either 1 or 0. So the XOR of same binary digit is always 0. So this will be 0. So we have H G transpose equal to 0. Okay. This is very important property. Very important property. Why? Look at this. You have C is equal to mg. This is how you generate the code word. Now if you multiply CH transpose on both the sides, H transpose, you get MGH transpose. But now MGH transpose, so GH transpose is 0, so you get 0. So CH transpose is 0. So it means that if a code word is a code word, then when you multiply it with H transpose, it becomes 0. How it is important, we will see it later. If there is an error, suppose you have a message M, you encoded it into code word C, then you transmitted this code word over the channel using usual modulation schemes, GPSK, QPSK, whatever. Suppose there is an error, you receive some C dash. Now whether there is error or not can easily be detected, because if C dash H is not 0, then definitely it is not a code word. So it means there is an error. And in fact, it will give us a way to correct the error also. So in next lecture, we will demonstrate things with examples. So in this lecture, things were general, don't worry. In next lecture, I will take example of particular code, define generator matrix, define parity check matrix, and also define something called syndrome decoding, how we can correct the error also.